All right, guys. So we want to start the new unit here. If you remember the last unit of the course, we started talking about inferential statistics and hypothesis testing, specifically how we would look at a sample of data and compare it to either a population of data, some characteristics we know about that population, or to another sample. Right, the goal being to test our hypotheses about how our independent variable might affect the behavior of one sample versus another. So to do a little bit of a conceptual refresher here of what we've discussed so far over the course of this couple of units, we've talked about standardizing the z distribution, right? We can take that with pretty much any distribution of raw scores, and then using the mean and standard deviation of those scores, we can see where any particular score is relative to the distribution in terms of standard deviation units. So is it one standard deviation above, one standard deviation below that mean, and so on and so forth, right? Anywhere in between and further up than one. All really giving us an idea of where that particular score sits in that larger distribution. Is it very close to the middle? Is it very far towards the extremes? We can also do this not just with scores, but with a sample average, right? We can create a distribution of means or a comparison distribution that says where all those hypothetical values would be, and then where our sample mean would be in that larger population of hypothetical values of the mean. So again, this is extremely helpful because it allows us to know percentiles, it allows us to know all sorts of information. Sorry, Kat really wants to teach statistics today. And it allows us to, more importantly, see the sort of relative frequency or likelihood of a given score or sample mean. When it's near the center of the distribution, we know that it's a relatively likely thing to have occurred. When it's far in the extremes, we know it's very unlikely to have occurred. And so if we did something to a sample that we think should have changed them to make them look different from the population, then we would be expecting to see something very different from what was likely to have occurred, and instead something that would be unlikely to occur due to chance alone, thus likely in support of our hypothesis. So we did this with the z distribution and the t distribution when we had single sample means, so we were comparing it to a population mean. We talked about a distribution of all those hypothetical values of the mean. When we were looking at a paired samples t-test, we took a sample of data from one group of individuals, then we measured that group of individuals a second time. We subtracted off the second score from the first score to create what we call a difference score. The null, of course, would predict that those difference scores would all be 0 because nothing would have changed their behavior from time 1 to time 2. So we compare whatever that average difference score is that we have to a distribution of mean differences, all those possible values of a difference score, right? And then finally, in the independent samples t-test, since we were looking at two completely different samples and there was no justification or ability to create a different score, we instead looked at a distribution of scores for one group and we got an average, a distribution of scores for another group, we got an average, and we looked to see how those two means differed, right? So a distribution of differences between means. All of these allow us to see how a difference we observe in our data, our samples, may or may not be something we would expect to have seen in the larger population, in order to then infer, right, inferential statistics, something about whether or not our samples came from the same population or if in fact they came from different populations. The other thing I want to point out is sort of the mathematical similarity between all of the formulas we've looked at. So I'm simplifying a bit here because I'm not showing you the independent samples t-test, but if you remember, it basically simplified down to basically the same thing. And so if we just look at the numerators of each of these, and again, the same thing in the independent samples t-test, we have a measure of the sample mean minus the measure of the population mean. Really, it's a difference between averages. It's a difference between the center points of these groups. Right? And we might call this between groups variance. How far does one group vary or differ from another group? In the denominator then, if we look at both of those, we see a measure of standard error, variability. This is how much inside of a group the individuals differ from one another, right? How much variance is there within a singular group? And so if the top is a measure of between groups variability, then the bottom is a measure of a within group variability. Really two measures of variability in a way. To sort of contextualize this, we might think that the numerator might represent the difference that there is between the average height of men and the average height of women. Were you to plot these two distributions and all of the various heights of men and all the various heights of women, we would expect then that the height of men would be slightly higher than the height of women. These two distributions would be largely overlapping, but that minor bit of difference in there would suggest that their peaks, their center points, do in fact differ. That's what we're talking about, that difference between groups, or that between groups variability. That's what the numerator really represents in all of these test statistics. In the denominator, we're talking about how all of the men and all of the women aren't exactly the same height. So all of the men in a distribution, just because men are on average taller than women, doesn't mean all of the men are necessarily taller than all of the women. And so for that reason, we see this distinctive difference here in variability. All right, apologies there for that brief interruption. My family's jerks. They are loud. All of us packed in one house is becoming a bit of a nightmare. Anyway, the denominator then being a measure of variability within a group, right? So to retrace, meaning all of the men in a particular distribution aren't necessarily taller than all the women in their distribution. There will be women that are taller than many of the men, just like there will be men who are shorter than many of the women. That variability within a group is being captured by the denominator. The difference between the groups is being captured by the numerator. And what we're looking at is to see whether the difference between the groups is larger than the spread of the individual groups, to see whether or not these are highly overlapping, or if in fact they're far enough apart that we could say they're likely for different distributions, right? Different populations. So, because what we've looked at so far has always been a measure of two samples at most, and we could certainly have situations where we're looking at three samples, right? Three different ethnicities, perhaps three different geographic regions of the country or the world, right? And so many variables have more than two levels. Because of that, we need a different way of performing a hypothesis test. Now, realistically, once you've learned the Anova, you don't ever have to use the t-test, because the Anova design actually can handle two group comparisons in addition to three group, four group, five group, and six group. But the single sample t, the one where you have a singular sample compared to a population t, is the only time you would still need to use that t-test. Okay, so as a refresher then, when we know the sample mean and the sample standard deviation, when you know the population mean and the population standard deviation, then we can compare our singular sample to that using a z-test. If we don't know the population standard deviation and we only know the population mean, then we can compare our single sample to it using a single sample t-test. In the cases where we have multiple samples, right, we have to figure out how many we have, and we may have two that are the same group measured twice, in which case it's a paired or dependent samples t-test. We may have two that are measured as different groups, in which case it's an independent samples t-test. In the case where we have three or more groups, we have to use the Anova design. But it too could be a between or within groups Anova design, just like we talked about with independent and dependent samples t-tests. Just like with a t-test, where it's a distance between two distributions and how much those two distributions separate or overlap, the F ratio that we use in the Anova is a measure of overlap of three or more distributions. Right? And so realistically, it's the exact same thing that we're doing. We just have to modify the formula a little bit to handle three groups instead of just the two groups we've had so far. And so why do we call it an F ratio? Well, it actually has to do with a guy named Sir Ronald Fisher, right? And he essentially realized that if the t-test handled hypothesis testing by using between groups variance relative to within groups variance, essentially a ratio of one measure of variability to the other, he saw no reason why you couldn't modify the design to handle that for multiple groups. And so in the Anova, the between groups variance is, just like with the t-test, an estimate of the difference between each individual group and pretty much their center point or average of each of these individual groups. So the differences between the means of your three samples, right, or four or five or six samples, however many there happen to be. Within groups variance, then, is a measurement of how all the individuals in a particular sample don't behave alike, right? There's variability. That distribution spreads out. And so we're going to have three measures of within groups variance, at least, for each of our three groups. And just like with our standard area of the difference, we need a way of packing them all together into a singular number in that denominator. And that's part of what the Anova design is intended to do. So you might ask, why do we need the Anova design? The Anova design maybe can do it in one test, but we know that we could have done this with a t-test. So if I gave you an example that said, do speech rates, the rapidity, the speed at which somebody speaks, does that differ between cultures? And so when I remember learning Spanish in elementary school, I heard some of the folks around me that could speak Spanish speaking so rapidly that I thought, man, Spanish speak really, really quickly. Now, while there is some truth to that, a lot of learning a foreign language is unfortunately realizing that it seems everybody speaks quickly when you don't know what they're saying, and that's part of the reason, excuse me, is because you can't tell where one word ends and another begins when you're not familiar with those words. If you go and analyze my speech, there's not a lot of pauses between words. Okay, so going back, do speech rates differ? So we can pick three big cultures: American culture, right? American English, we can measure those speech rates. Japanese culture, tend to be thought of as a relatively quick speaking culture, so we should expect them to be relatively fast relative. It's multiple relatives compared with the United States. And then finally, the Welsh language is thought to be somewhat slower. And so it's possible then that Welsh speech rates differ from American speech rates. So if I wanted to run t-tests, I could run the test between Japanese speech rates and American speech rates, and then another one between Japanese speech rates and Welsh speech rates, and then another one finally between American speech rates and Welsh speech rates. And then all three t-tests would have given me all the various paired comparisons that I would need. Right? That would be one way of potentially solving this. Really, in reality, we're still talking about the same idea. Not all Americans speak at the same rate. I probably speak much more quickly than some others, and there are probably people who speak even more quickly than I do. And thus there's some variability, some within groups variance among Americans, just like there's a within groups variance in speech rates among Japanese, and there would be some within groups variance, among the speech rates of Welsh. Right? All of these speech rates are going to differ within those groups, and that's our within groups variability. But we should also be able to see if it exists an overall difference between one group and another group as measured as the difference between the means of those three relative groups. If the difference between the means of the groups is larger than the difference within each of the groups, then potentially we have a significant difference in speech rates between these countries. Again, a measure of overlap. Now, why don't we run just those three t-tests instead of running the Anova? Part of it comes back to the idea of our alpha level or our p-value. Remember that we have decided in behavioral sciences that an acceptable risk of a type 1 error, right, the probability of rejecting the null when the null happened to be true, would be 0.05. We're willing to take a 5% risk that when we conclude that our hypothesis is true and we reject the null instead, we are taking a 5% risk that we are wrong, a 1 in 20 chance that we are wrong. That's acceptable within behavioral sciences because a lot of what we do is not life or death, and a 1 in 20 chance of being wrong is still relatively small. In cases where we might be determining the efficacy of a surgical procedure that could result in death if it went awry, we might want to use the p-value that's considerably smaller, right, that takes a much lower risk of error. Now, let's go back to the t-test idea. If I were to run a singular t-test and I used a p-value of 0.05, that means that whatever I determine, I'm taking a 5% risk that I'm incorrect. If I were to run a second t-test, I'd have a 5% risk that I'm incorrect in that test as well. And so if I have multiple t-tests combined, as we have in the situation where we would look for a difference between America and Wales, or a difference between America and Japan, or a difference between Japan and Wales, well, when you add those probabilities over the course of those different comparisons, you have to add the p-values for each one together. And so for three t-tests, we would be close to, it's not exactly there, but close to a 15% risk of a type 1 error. Because each t-test had a 5% risk and there were three tests, we've now inflated our risk of type 1 error across our experiment considerably. In this case, a threefold factor, right? Jumping up to 15% risk of error. If behavioral sciences has said that it's okay to have a 5% risk of error, it certainly has not said that it's okay to have a 15% risk of error. And the reason why I say this thing about the fishing expedition is that many times people will run many comparisons, not knowing that this increases the risk of error. If you were to run 15 to 20 comparisons, then statistically speaking, you are highly likely to find one of them to be significant, and it be because of a type 1 error. When you run the risk of a type 1 error that goes up to 60, 70, 80% likely to occur, that's more likely that one of your conclusions is wrong than that none of them. And you can kind of see how quickly this can inflate. If we just have two samples and two means, then it's just one comparison. We set our p-value at 0.05 and we are just fine. But in the case where we have three means or four means or 5, 6, or 7 means, you can see with 7 means you would need 21 comparisons. And for 21 comparisons, your probability of a type 1 error, if you were just running t-tests, would be about 66%, right? Considerably higher than the risk we are willing to take in behavioral sciences. So we're only going to talk about one type of ANOVA today, but I want to introduce to you the multiple types that exist. So all the ANOVAs that I'm going to ask you to actually calculate will involve only a singular independent variable being manipulated. It'll either be manipulated in a between subjects way, where different groups experience different levels, or it'll be manipulated in a within groups way, in which case all individuals experience all levels just at different time points in the experiment. This is why we're going to call our ANOVAs one-way ANOVAs. If you had two independent variables, you'd call it a two-way. And with three, you call it a three-way. And then after that, we drop the number and we call it a factorial ANOVA, because another name for an independent variable is a factor. The other thing that we have to describe our ANOVA with is how our independent variable is being manipulated. And so in the case where we have the different groups experiencing different levels, we call that a between groups one-way ANOVA. In the case where our different groups are really the same people being measured at different time points, a repeated measures of dependent design, we call that a within subjects one-way ANOVA. So like I said, you're only going to have to calculate the between groups ANOVA on the exam, and you're only going to have to calculate between and within on homework. I'll introduce the two-way ANOVA in order to introduce what's called an interaction, but you will not actually have to calculate that one on a homework assignment or on an exam. Okay, so the assumptions of an ANOVA, just like any hypothesis test, because we are assuming something about a population based on sample data, we have to meet a handful of essential assumptions that are tied to the test itself. The assumption we're familiar with, data are selected randomly, population is normally distributed. Remember that as long as we have sufficient sample sizes, then we could count on this one being met because of the central limit theorem. And then a new one to ANOVA, because the ANOVA requires multiple groups, 3 or more groups. We are looking to see that the variability of each of those groups, so the spread of, let's say, male heights and the spread of female heights, that spread in each of those two groups is approximately equal. It's what we might call homogeneity of variance. If that's the variance of one group, the variance of the other group, we want them to be about the same, homogenized, right? Like homogenized milk mixes all the various batches so that it all tastes the same. So same variance. Another term for that is homoscedasticity. Homoscedasticity. If you don't have homoscedasticity, you have heteroscedasticity, right? So prefixes that we're relatively familiar with, so you should be able to reason these ones out. What's the rule of thumb? How do you determine whether variances are equal? Because they're highly unlikely to be the exact numeric value. Well, when you have equal sample sizes, so in a between groups design, it's possible that you'd have 7 people in the group of males and 5 people in the group of females. That different samples, when you have different size samples, then what you have to do is compare the smallest variance, so the variance of the smallest group, to the variance of the largest group, right? The largest variance, that is, excuse me, not sample size, but the largest variance you calculate, to the smallest variance you calculate. And as long as the largest variance is less than 2 times the smallest variance, then you have met this assumption. So you find your smallest variance, you multiply it times 2, and as long as the largest variance is less than that, then you've met the assumption. If you have equal size samples, well, then you have even more leeway. It's okay if the largest variance is less than 5 times the smallest. So you find your variances again, you take your smallest, you multiply it times 5, and as long as your largest variance is below that, you've met the assumption. So we'll talk about how to calculate that when we get to a particular example with numbers, but that is your new assumption for the between groups ANOVA design. Again, what do I mean by homoscedasticity and heteroscedasticity? If you look at these two distributions, you can see that their spread is very different. You can see the numerical scales line up just fine, but in the top example, most of the data fall between about 3 and 3, whereas in the bottom, the data fall between about -5 and +5. So the latter has far more variability than the top one does. This would mean that these two distributions were heteroscedastic, and you would not be meeting the assumption for this particular ANOVA. We want to look for homoscedastic designs where that spread is approximately equal. Why? Because the entire point of an ANOVA is to see how these distributions overlap. If you have less overlap, you have a significant difference between your groups. If you have a lot of overlap, then it's saying that those samples all came from the same population and not different populations. Right? And so if you look at the top set of distributions, you have a large within group variability. Each group is spread out relatively wide, but then you also have small between groups variability. This is a large denominator and a small numerator, right? The groups are very close together and they're spread out, so they're highly overlapping. In the second group, we keep the exact same measure of within-group variability, right? Each group's still relatively spread, but we increase the between-groups variability. And you can see far less overlap in this case. And then the last situation where we have very small within-groups variability, and we then have reasonable, let's say moderate to large between-groups variability. I apologize if it's written incorrectly there. We will then have less overlap, right? And that less overlap means that we have samples that came from different populations, which means we can reject our null hypothesis and that there is a difference between these groups, right? And so that's the ideal, trying to quantify overlap. In order to measure overlap, you need to make sure that the spread between the groups is approximately equal. So to sort of get at where we're going to be then mathematically, remember that the F ratio is a measure of between groups variance over within groups variance, right? A ratio of the difference between the groups to the difference within each of these groups, which means that if the difference between the groups and the difference within the groups is approximately the same, as we saw when there was complete overlap, then we would expect an F ratio of something close to 1. Whatever was on top was pretty close to whatever was on bottom, and the difference between the groups was as much as the error or spread within each of the groups, and thus an F ratio of 1 is unlikely to say anything about a significant difference between our samples. Any F ratio above 1 is where we're starting to talk about potentially a statistically significant difference. Just like with our previous tests, we need to find out what our critical comparison value would be. It may be a 3, a 4, a 5, depending on our degrees of freedom, and we compare our obtained F ratio to that critical value in order to determine if we have greater between groups variability than would be expected due to chance alone, and thus likely a difference between our various samples. So I think this essentially covers some of that, but the one thing I want to add to that then is that if you think about the way these are being compared, within groups variability would be just like with standard error of the difference with a t-test. We'd measure the variability of one group, the variability of another group, the variability of another group, and that's how much each of the individual scores, raw scores, differ from one another, right? And differ from one another in each of these groups. And then we find a way of packing them all together like the standard error of the difference. But it's still a measure of how much individual scores differ from other individual scores. When we talk about between groups variability, we have our distributions, but now we're talking about how the average of this one differs from the average of this one. The average is not the same as a raw score, right? It has far less variability because it has many scores that contribute to it. It's an amalgam or a statistic that describes the scores. And so it's sort of a different level of comparison, an apple to an orange almost, if you will, which means the top numerator is measuring a difference between means, and the denominator is measuring a difference between individual scores. And so that requires a little bit of correction in the math itself.